Here we've been asked to work out, again, Kp, another Kp calculation. I've been told that I've got 2 moles of sulfur dioxide and 1 mole of oxygen. They're mixed and allowed to reach equilibrium with a pressure of 5 times 10 to the 5 pascals. And at equilibrium, I've got 0.67 moles of oxygen. And we've got to work out Kp. Well, firstly, we've got to do a Rice table to work out the number of moles of each component at equilibrium. I've been told that I've got 2 moles of SO2 and 1 mole of oxygen, and we always assume, if we're not told otherwise, we've got 0 moles of the other component in the mixture. Now, at equilibrium, I've got 0.67 moles of oxygen, so this means this must have decreased by 0.33 moles. This means this has decreased by 0.66 because it's a 2-to-1 ratio, so this has gone down by 0.33 times 2, and that gives me at equilibrium 1.34 moles. This would have therefore gone up by 0.66 to give me 0.66 moles at equilibrium. Now, let's just write my expression for Kp. Kp is equal to the partial pressure of SO3 squared divided by the partial pressure of SO2 squared times by the partial pressure of oxygen. Remember, no square brackets anywhere in sight when writing this expression for Kp. So we've got the moles at equilibrium here. We need to work out the partial pressures. And if we looked at the previous video, calculating Kp1, we should be able to do this. First thing we do is work out the mole fractions. And so the mole fraction of, we'll do SO2, remember, is equal to the moles of SO2 divided by the total moles. So the moles of SO2 is, as you can see from the Rice table, is 1.34. 1.34 then divided by the total number of moles, which remember is these moles values added together. That gives me 2.68 when you add them together, and it gives me a mole fraction of 0.5. And we can repeat the same procedure with the other components in the mixture. So let's just do that. So the mole fraction of oxygen is moles of oxygen divided by total moles. Moles of oxygen is 0.67. So that's 0.67 over 2.68, and that gives me 0.25. And again, if I do the same thing, this time I want the mole fraction of SO3, which is now 0.66, and that should give me just under 0.25, 0.246. So these are my mole fractions, and these should add up to 1. I think it's just slightly under. I think it's because in reality I think these should both be 2/3. Should be both 0.66 recurring. We then have to work out partial pressures, and we should be able to remember from the previous video what partial pressure is. Partial pressure, remember, is mole fraction times total pressure, that's partial pressure. We've been given in the question the total pressure, it's there, so we multiply each of these by 5 times 10 to the 5. And when you do that one, you should get 250,000. This gives you 125,000. And this will give you, again, just a touch under 134. Okay. So these are all my partial pressures, and then it's a case of putting those partial pressures into your Kp expression. So when we do that, we get the partial pressure of SO3, 123,134. And again, that has to be squared, divided by the mole fraction of SO2, which is 250,000. Again, that needs to be squared times 125,000, which is the partial pressure of oxygen. And it's just a case of putting those numbers in your calculator. And when you do that, you should get an answer of 1.94 times 10 to the minus 6. Again, the units, well, the units, if you think about it, these pascals squared, cancel these pascals squared. So the units for these are simply pascals to the minus 1. And that there is your answer. Again, in these sort of questions, please show all your working, show your rise table, show your mole fractions, show your partial pressures, and then populate your Kp expression with your partial pressures and give the answers with the units.